Tonight's journey drifts into the quiet power of luminous blue variables, massive stars that shed matter in slow-motion eruptions. Each outburst builds a glowing shell. Each shell cools clumps and fades into the wider darkness. From braided rims and shadowed knots to dusty lanes and softened halos, these nebulae become gentle records of change across thousands of years. If this kind of calm cosmic storytelling is your thing, please hit like and subscribe. It helps the channel grow and it lets more long-form sleep science arrive right on time. A luminous blue variable rests near a boundary where brilliance becomes a physical force. Light pressure in the outer layers can lift gas and begin slow eruptions that later become nebula shells. The opening image is calm and steady. A blue-white glow sits inside a pale haze. The haze thickens and thins over years. Its edge grades from bright to dim through a broad rim of scattered light. Some luminous blue variables shine about 1,000,000 times the sun's brightness. The glare resembles noon sky condensed into a single point of light. Even at great distance, the glow does not look like a point. It looks like a soft sphere with a wide halo. The halo is not decoration. The halo is matter in motion. At this distance, the star does not present a hard surface. Light behaves as if it comes from wherever gas becomes only barely transparent. When the outflow thickens, that boundary moves outward. The star appears to grow larger without changing the core. The glow becomes a swollen sphere with a brighter center and a dimmer edge. The edge is the zone where photons scatter and change direction. A simple conclusion follows from this geometry. The visible surface is often not the star at all. The visible surface is the wind itself glowing where light finally escapes. The wind can hide the core and replace it with an apparent face. The face can brighten and fade while the underlying core changes less. The outer layers then resemble a slow sea of light with a rim that breathes outward and inward over time. One concept governs the balance behind this behavior. The Eddington limit means light pressure balances gravity. Near that limit, a small change in opacity can tip the scale. Opacity is how easily light is blocked by matter. When opacity rises, radiation lingers longer in the outer gas. That trapped radiation pushes outward more strongly. The gas expands and cools as it lifts. The expansion can raise opacity again in some layers. The cycle can feed itself for a time. A natural comparison holds the feeling without borrowing machinery. A warm-up draft holds a bank of fog above a cold slope. When air warms and rises, fog thickens and spreads. When air cools and settles, fog thins and breaks. In a luminous blue variable, the outer gas can behave like that fog. It thickens when conditions favour more blocking. It thins when conditions favour more escape. The difference is scale and consequence. In fog, the boundary shifts across a hillside in hours. In a massive star, the boundary can drift over years and reshape a whole surrounding region. A second concept shapes the bright phases and the apparent size. A dense wind can form a pseudo-photosphere. A pseudo-photosphere is an apparent surface inside the outflow. It forms where the wind becomes thick to scattering. Photons change direction many times before escape. The last scattering layer becomes the place that seems to glow. The wind is not smooth. It carries clumps and streaks, some are denser sheets, some are rare gaps. Those variations create subtle mottling across the rim. A concrete physical detail anchors the scene. The apparent disk has a softer edge than a solid sphere. Brightness fades through a gradient rather than ending sharply. The gradient marks a depth range where scattering still matters. In that range, light does not travel straight outward. It wanders. The wandering spreads the glow into a halo. The same wandering also hides fine structure in the core. The visible face is a moving veil. The veil is real matter with real thickness. A third concept explains why a shell remains after the wind calms. In a rare outburst, mass loss surges for a time. A thicker wave of gas runs outward into older wind material. The collision draws a moving boundary. That boundary compresses into a thin rim where density piles up. The interior behind it becomes more rarefied. The rim cools faster than the interior. Cooling increases contrast and encourages clumping. A faint oval shell then drifts outward, like an eggshell ring around a dim interior. Its front edge brightens into a thin arc. The arc looks sharper than the haze near the star. The sharpness comes from compression. The rim gathers matter into a narrower layer. A layered structure forms rather than a clean bubble. The rim is one layer. Behind it lies a thicker zone of mixed gas. Farther in lies a region where light scatters through lower density material. Each layer has its own transparency. Each layer shapes how the nebula looks from afar. Physical detail keeps the picture grounded as the rim travels outward. Knots form where denser clumps resist mixing. Each knot lags behind the main front by a small amount. Each knot casts a faint shadow into the interior by scattering light away. The interior can look dimmer because photons have fewer scatterers to redirect them. The shell can show wrinkles where instabilities crumple the boundary. It can show a thicker band in one direction and a thinner band elsewhere. The rim can break into beads along an arc. Those beads can merge into filaments as the shell stretches. A gentle scale shift follows these details outward. Near the star, the forming rim belongs to the same neighborhood as close-orbiting planets. Farther out, the same rim becomes a structure measured in distances where even starlight takes years to cross. The shell keeps expanding long after the outburst ends. The outburst is an episode. The shell is a record. The record can outlast the conditions that formed it. A limit of intuition and observation arrives with the hidden core and the filtering wind. When the pseudo-photosphere forms, the true stellar surface cannot be seen directly. Only escaping light and shell geometry carry clues. Scattering smooths sharp features and blurs boundaries. Clumps can mimic changes that are not real shifts in the core. Dust can dim some wavelengths more than others. Inferences then depend on models of opacity and ionization. Those models can agree on orders of magnitude. They can still miss the exact mass and timing of a surge. The same light that reveals a shell also hides the launch details. The shell becomes a slow message written in gas. The message is readable in broad strokes. Fine handwriting remains uncertain. The section closes with a gentle transition. Nebula shells grow out of years of quieter variability. Brightness and color drift as wind density changes. Apparent size swells and recedes with the pseudo-photosphere. After that, the slow cycles come forward in the same calm light. The wind's steady breathing sets the stage for lasting geometry. A luminous blue variable changes with a patience that matches the slow drift of seasons in space. Much of the visible variability comes from a shifting apparent surface as the wind thickens and thins. The opening image is quiet color and a softened edge. A blue-white core holds steady at the center. A wider rim around it turns milky and diffuse. The rim does not end sharply. It fades through a smooth gradient where light scatters. In that region, light behaves as if it leaves from a cloud rather than from a wall. The boundary of last scattering slides outward and inward, across years. That sliding boundary makes the star seem to grow and shrink. A single number frames the tempo. One broad cycle often spans about 10 years like a tree, adding one clear growth ring. In that time, the outer flow can rearrange itself many times. It can also carry the imprint of change far from the star. The first unlock is simple. The star can look cooler and larger without gaining new fuel. The change happens in the outer layers and in the wind. Opacity guides that change. Opacity means how strongly matter blocks light. When opacity rises, radiation spends longer inside the outer gas. That trapped radiation pushes outward more effectively. The outer layers expand. Expansion spreads the gas and cools it. Cooling can increase opacity in some layers. The balance then tips toward an even thicker wind for a while. A calm visual anchor holds the mechanism in view. The star appears wrapped in translucent bands that stack like thin sheets of milk glass. Some bands look denser and brighter. Some look thinner and bluer. Between them, faint gaps appear as darker lanes. Those lanes are not empty. They are simply less crowded with scatterers. As density rises, the apparent surface moves outward into a cooler zone. As density falls, the apparent surface retreats inward into a hotter zone. The visible color drifts with the boundary. Blue slides toward white. White slides back towards blue. The second unlock follows from where the energy emerges. Total power can remain near steady while visible light changes a great deal. When the apparent surface cools, more emission falls into visible wavelengths. Brightness in the visible can rise even if the core output stays similar. The shift is not a new engine. It is a reshuffling of the same luminosity across color. A subtle detail appears at the limb during these swings. In cooler phases, the limb looks more extended and more even. The gradient spreads the light into a wider skirt. In hotter phases, the limb contracts and the center brightens relative to the edge. The disk looks smaller but more intense. This is the same wind seen through different thickness. A small change in opacity produces a large change in appearance. The effect resembles a thin film of frost that turns from white to clear when warmed. The water remains present. Only the scattering from countless tiny surfaces changes. A single analogy keeps the intuition soft and concrete. A tide line creeps up and down a quiet beach. The ocean remains present even when the edge retreats. The tide line is only the place where water finally shows itself on sand. In the same way, the pseudo-photosphere is only the place where light finally escapes the wind. A pseudo-photosphere is an apparent surface formed in an outflow. It is not a solid boundary. It is a depth where scattering becomes rare enough for escape. Physical detail keeps the tide line grounded in stellar matter. The wind holds a density gradient that declines with radius. It is a ramp, not a step. When the ramp steepens, photons bounce more times before leaving. The rim becomes broader and softer. The center loses sharpness. When the ramp relaxes, photons travel more directly. The rim tightens. The center looks clearer. Small clumps ride inside the flow. Each clump can brighten a patch by adding scatterers. Each clump can dim a neighboring patch by redirecting light away. The visible face becomes mottled in slow motion. Another quiet payoff appears in the motion of the bands. Thicker layers drift outward and thin as they go. Thinner layers follow behind and catch up less easily. Layering builds a faint pattern of arcs around the star. Those arcs are early sketches of a future shell. Scale shifts arrive when the mind follows one arc outward. Near the star, the shifting boundary moves across a small fraction of the radius. Farther out, the same change becomes a difference in the wind density that fills an enormous volume. Over a decade, that altered wind can reach distances larger than the span of a planetary system. Over many decades, overlapping cycles can stack into a broad envelope. The envelope becomes the stage for a later eruption. It sets where shocks will compress and where cavities will open. A limit of intuition enters with the hidden core. The true stellar surface cannot be seen when a dense wind dominates the last scattering. A distant signal then carries only combined color and brightness. It cannot directly reveal where each photon last changes direction. Dust mixed into the outflow can also redden the light. Clumping can mimic a cooler surface without a true temperature shift. Interpretation depends on models of opacity and ionization. Those models are strong in order of magnitude. They are weaker in fine detail. Mass loss rates and radii can trade places inside a fit. Different combinations can produce nearly the same glow. The uncertainty is not failure. It is a reminder that the visible surface is a moving veil. A final visual anchor returns the section to calm geometry. A pale ring forms where the gradient steepens. The ring looks like pearl light smeared into a halo. It thickens slightly, then thins. Faint striations inside the halo drift outward like slow ripples across water. Each ripple marks a modest change in density. Each ripple carries the memory of a cooler or hotter phase. The surrounding space becomes gently structured by these cycles. The closing movement turns from appearance to preparation. Slow variability lays down a layered wind and a shifting pseudo-photosphere. That layered wind becomes the medium that any stronger surge must cross. Next, the steady radiative driving of the wind comes into focus. From that steady push, heavier episodes of loss can emerge without sudden violence. A steady wind leaves a luminous blue variable long before any rare eruption draws attention. The wind is driven by light that transfers momentum to the outer gas. The scene begins close to the star where the glow meets a moving skin. A thin veil streams outward and carries faint striations. The striations curve into shallow spirals as rotation subtly shapes the flow. At this distance, light behaves as a pressure that can push on atoms and ions. The first unlock is that a wind can exist without an explosion. The star's luminosity is enough to keep matter lifting away each moment. The push comes from countless interactions between photons and matter. Some interactions are simple scattering, others are more selective and occur at specific colours. Line driving is radiation pressure absorbed in many spectral lines. It acts like a wide comb of tiny catches across the light. Each catch transfers a small kick to the gas. Many small kicks add into a steady outward drift. The wind is not uniform from the start. It forms narrow streams where driving is strong. It forms softer lanes where driving is weaker. The boundary between streams becomes a place where density gathers. A clear physical detail appears along that boundary. The gas shows layered sheets with sharper rims. The rims mark compression, where faster material catches slower material. The layered sheets drift outward and thin. Their edges stay visible longer than their interiors. The second unlock is that the wind itself can sculpt the future shell. A denser wind builds a thicker ambient medium. A thinner wind leaves a more open cavity. Later eruptions move through what the wind already laid down. The wind becomes the background that decides where shocks brighten. A slow visual anchor holds the wind in motion. A faint cone of outflow extends from the star. The cone is not solid. It is made of nested translucent skins. Each skin carries a soft gradient from brighter inner edge to dimmer outer edge. The gradients come from changing density and changing scattering. A darker notch appears where the flow is slightly more rarefied. The notch is not a hole. It's a corridor with fewer scatterers and more direct light. In that corridor, the star's core glow looks sharper. Outside it, the glow looks spread and milky. The wind's speed sets how quickly the scene changes far away. A typical fast wind can reach about 1,000 kilometers per second. That pace resembles crossing the distance from Earth to the Moon in only several minutes. In a few days, such a wind crosses the distance comparable to the orbit of a close inner planet. In a decade, the same flow fills an enormous volume around the star. The scale shift is gentle but relentless. A motion that begins near a photosphere becomes a structure spanning many billions of kilometers. The wind also carries a hidden pattern in its density. Small clumps form because driving is not perfectly smooth. Some clumps are denser than their surroundings by a large factor. Clumping changes how light escapes. It also changes how mass loss is inferred. The third unlock is that a wind can look heavier or lighter depending on clumpiness. A smooth wind spreads matter evenly and blocks light predictably. A clumped wind hides mass in dense pockets. Light can leak through rare gaps between clumps. This leakage is sometimes called porosity in the flow. The word describes how empty lanes reduce effective blocking. The idea is simple in plain language. A sponge holds water in dense strands while leaving holes. Water can still pass through the holes quickly. In the same way light can pass between dense clumps, that passage can make the wind appear thinner than it truly is. A new analogy grounds the effect without repetition. It is like a thin curtain made of many beads. The beads can cluster and leave wider openings. From far away, the curtain may seem almost transparent. Up close, the beads still carry substantial material. The wind then becomes a curtain whose transparency depends on texture. The physical consequence is visible in the rim. The apparent edge can sharpen when gaps allow deeper sight. The edge can soften when clumps multiply and scatter more. A calm visual anchor returns with more detail as the wind travels outward. Thin arcs appear where compressed layers pile up. The arcs are incomplete circles with brighter tips. The tips mark places where the line of sight crosses more material. Between arcs, faint wash-like light fills the volume. The wash is scattered starlight and faint emission from energized gas. The arcs drift outward like slow ripples that never break. Each ripple marks a change in driving or density at the star. Each ripple is a memory of a brighter phase or a denser phase. The rhythm of these ripples supports a quiet payoff. The wind is not only loss, it is also writing. It writes rings and arcs that can be read later as a timeline. A limit of observation enters with the same clumping that makes the wind interesting. Mass loss is not weighed directly in most cases. It is inferred from light that passes through the flow. Different wavelengths sample different layers. Some trace dense clumps and some trace smoother regions. Ionization also changes with distance and density. A signal would carry mixed information from temperature and from structure. Two different wind textures can produce similar brightness. Distance uncertainty can also shift inferred luminosity. Model assumptions then matter. Smooth wind models can overestimate mass loss if clumping is ignored. Highly porous models can underestimate mass loss if gaps are exaggerated. The limit is a limit of inference rather than a limit of physics. The wind exists regardless. The measurements describe it only through filters. The uncertainty remains even when the broad behavior is clear. Another gentle payoff follows from this limit. The most reliable conclusions often come from the wind's geometry. The shape of arcs and the thickness of rims constrain where compression occurs. Those shapes are less sensitive to some spectral ambiguities. The geometry also sets where a future eruption will brighten into a shell. When a denser surge arrives, it runs into the layered wind. It shocks at the arcs and thickens them into sharper rims. It also sweeps the wash into a clearer cavity behind the front. The closing image stays slow and stable. The translucent skins continue outward. Their edges remain faintly brighter than their centers. The darker notch persists as a softer corridor through the haze. The star remains hidden behind its own moving veil. The next step follows naturally from the balance that makes the veil possible. Near a brightness threshold, light pressure can nearly match gravity. That threshold shapes when the wind remains steady, and when the outer layers begin to lift more dramatically. A luminous blue variable carries a quiet tension between falling inward and being pushed outward by light. That tension rises because light pressure can approach gravity in the outer layers and make the atmosphere easy to lift. The opening image holds close to the star. A bright core sits inside a smooth pale envelope. The envelope shows a faint seam where brightness drops into a softer gradient. The seam is not a crack. It is a depth where scattering begins to dominate and edges blur. At this distance, light behaves as a steady outward nudge that never turns off. The first unlock is simple. When light pressure nearly matches gravity, a small change in opacity can change the wind dramatically. Opacity is how strongly matter blocks and scatters light. Higher opacity traps radiation longer in the outer gas. Trapped radiation deposits more momentum. The gas is pushed outward more easily. Lower opacity lets radiation escape more directly. Escape reduces the push and allows settling. This balance is often described with the Eddington limit. The Eddington limit is where radiation pressure balances gravity. Near that limit, the outer layers become lightly bound. The outer atmosphere can inflate without a violent trigger. A second unlock follows from the same boundary. The star can move closer to that limit without increasing its core power. A shift in opacity can raise effective radiation pressure in specific layers. Opacity can change when temperature shifts slightly. Ionization changes which atoms absorb and scatter. In those layers, the envelope expands and cools. Cooling can raise opacity in a band. The band becomes a thicker curtain of scattering. The apparent surface then moves outward into cooler gas. Brightness in visible light can rise even if total luminosity stays similar. A slow visual anchor holds the change in shape. The pale seam becomes a broader belt around the star. The belt is brighter along its inner edge. It fades outward through a smooth gradient. The belt thickens for years. The star seems larger and softer at the rim. Then the belt thins. The rim tightens. The core looks sharper again through a clearer path. A physical detail remains steady through these cycles. The limb never ends sharply. The limb always has a fading edge where photons scatter and wander. That wandering is the signature of a wind that replaces a solid surface. The third unlock explains how this calm threshold can lead toward a more forceful episode. A wind that strengthens also cools as it expands. Cooler gas can allow more opacity in some layers. More opacity strengthens the push again. The feedback can amplify over time. The amplification does not need a sudden impulse. It needs sustained conditions near the limit. The process resembles a sand dune crest near its slipping angle. The dune holds shape for a long time. Grains still shift and creep. A small change in wind can push the crest past stability. The crest then slides in a smooth sheet. In a luminous blue variable, the sliding is not sand. It is gas losing its hold on the star. The atmosphere can drift into a denser outflow state. The outflow can then carry far more mass than before. The change can be gradual in time but large in effect. The surrounding space begins to fill with thicker layers. The thicker layers later become the material a shell will compress. A calm checkpoint arrives in the wind's geometry. When the star is nearer the limit, the wind can become slower and denser in the inner region. Denser flow increases scattering close in. Scattering spreads light into a wider halo. The halo becomes smoother and more opaque. In the outer region, older wind continues outward and thins. A layered structure forms naturally. Near the star there is a dense zone with a soft edge. Farther out there is a lower density zone with faint arcs. The interface between zones can become a gentle boundary. It can appear as a dim ring that surrounds the brighter inner haze. The ring is not a separate object. It is a transition in density and ionization. Another payoff arrives from the role of mass. Many luminous blue variables begin as very massive stars. A typical one can carry about 20 times the Sun's mass. That is like the mass of 20 suns gathered into one sphere. Greater mass deepens gravity. Greater luminosity increases radiation pressure. The tug and push grow together in massive stars. That pairing makes the threshold reachable. It also makes the outcome sensitive to small shifts in outer conditions. The same mass that binds the core can still leave the envelope lightly held. The envelope is where opacity rules. The envelope is where light can win. The scale shift is gentle but clear. A change in microscopic ionization states alters opacity. That microscopic change reshapes a wind that fills billions of kilometers. Over decades it sculpts a nebula that can span a region where light takes years to cross. A limit of observation appears where the threshold is most important. The Eddington ratio is not measured directly in most cases. It is inferred from luminosity and mass estimates. Luminosity depends on distance and on how the wind redistributes light across colours. Mass depends on models of stellar structure and on how rotation and mass loss evolved. Opacity in the wind depends on clumping and ionization. Those are inferred from spectra and brightness changes. Different combinations of clumping and mass loss can reproduce similar light curves. Different distance estimates can shift luminosity significantly. The limit is a limit of inference and resolution. The wind scattering smears sharp features. Fine structure in the inner flow is blurred into a smooth glow. The true surface remains hidden behind a moving veil. In that veil, a denser layer can mimic a cooler surface. A clearer gap can mimic a hotter surface. Without direct access to the inner boundary, models remain partly degenerate. The uncertainty does not erase the threshold. It only softens the precision of the numbers. The threshold still shapes what is plausible. It still explains why small changes can produce large visible swings. A final visual anchor gathers the section into one calm image. The star sits inside a pale dome of light. The dome has a thicker band that slowly migrates outward. The band leaves behind a dimmer cavity. The outer edge of the dome shows a smooth gradient rather than a rim. The gradient marks scattering that fades with radius. The dome breathes in apparent size over years. The deeper engine remains unseen. The closing movement points forward without sharpness. Near this brightness boundary, a denser wind can build a false surface that dominates appearance. Next, that false surface becomes the main stage. It turns a star into a glowing sphere of its own outflow and prepares the conditions for a lasting shell. A luminous blue variable can look like a star wrapped in its own calm weather. The apparent surface often forms inside the outflow and not at the true stellar boundary. The opening image is a bright core inside a smooth cocoon of light. The cocoon has a clear inner rim and a wide outer fade. The fade is a gradient where brightness slips into faint haze. In that region, light behaves as a traveller that changes direction many times. The first unlock is that the visible disk is a depth and not a wall. Photons do not leave from one sharp layer. They last scatter across a range where the wind becomes thin enough. That range acts like a soft shoreline for light. A pseudo-photosphere is an apparent surface formed in an outflow. It appears where the wind turns from opaque to transparent. When the wind thickens, that apparent surface moves outward. When the wind thins, it retreats inward. The star seems to breathe in size without changing its core radius. A calm visual anchor holds this motion. A pale sphere floats inside a larger translucent sphere. The inner sphere is brighter and sharper. The outer sphere is dimmer and more diffuse. Between them lies a thin, bright belt where scattering still dominates. The belt curves around the star as a smooth ring. It is brightest where the line of sight crosses more material. It fades where the path is shorter. This geometry is simple and it explains much of the variability. The second unlock follows from a single comparison in scale. The apparent radius can reach several hundred times the Sun's radius, like a sphere that could span an inner planetary orbit. That expansion is not a rigid balloon. It is a moving depth inside flowing gas. Optical depth sets where the last scattering happens. Optical depth is the number of scatterings along a path. When optical depth is high, light is trapped and wanders. When it is low, light escapes more directly. The wind carries an opacity gradient that declines outward. The gradient is not smooth in detail. Clumps and sheets add texture to the fade. Each clump thickens the local scattering depth. Each gap thins it and opens a clearer channel. As the pseudo-photosphere shifts, the star's colour and apparent temperature drift. A cooler apparent surface shifts more emission into visible light. A hotter apparent surface pushes more into ultraviolet light. The total luminosity can stay similar, while the visible brightness changes. This resolves a quiet question. Visible brightening can come from redistribution, rather than from new energy. A new everyday analogy keeps the idea grounded. A river carries silt that settles into a sandbar. When flow slows, the sandbar rises and widens. When flow quickens, the sandbar erodes and narrows. The river remains present in both cases. The visible edge is the sandbar and not the whole river. In the same way, the visible edge of the star is the pseudo-photosphere and not the whole atmosphere. Physical detail deepens the picture beyond the analogy. The wind can form a layered structure with a denser inner zone. That zone can be cooler and more opaque. Farther out, the wind becomes thinner and more ionized. Between them, a transition layer develops where scattering is frequent. In images, that layer would appear as a broad limb with no hard edge. In spectra, that layer would smear line profiles and soften sharp features. The third unlock is that a pseudo-photosphere can hide the very changes that create it. When the wind becomes thick, the true surface disappears behind scattering. The core temperature and radius become indirect quantities. Only the escaping radiation and the geometry of the haze remain. At this distance, a signal would mix many depths into one smooth glow. The wind also shapes the future nebula shell. A denser wind means more material close in. Later, ejecta must plough through that material. The first compression then happens at a smaller radius. A thinner wind leaves a wider cavity. Later, ejecta expands longer before it meets strong resistance. Either way, the pseudo-photosphere is the inner boundary of a larger story. Another visual anchor arrives on a slower scale. The cocoon shows faint concentric ripples in brightness. Each ripple is a weak density wave in the wind. The ripples drift outward and broaden as they travel. The inner ripples are tighter and brighter. The outer ripples are wider and dimmer. Together they resemble translucent growth rings made of light. Each ring marks a period when opacity and mass loss shift slightly. This provides a steady payoff. The wind writes a timeline in its own scattering layers. Following one ripple outward introduces a gentle scale shift. Near the star, the ripple begins as a small change in ionization. Farther out, the same ripple becomes a structure spanning billions of kilometers. Over decades, many ripples overlap into a thickened envelope. That envelope becomes the centre for a future shock front. A limit of intuition and observation appears at the heart of the cocoon. The pseudo-photosphere blurs cause and effect in the light curve. A brighter visible phase can mean a cooler apparent surface. It can also mean a denser wind that spreads light more efficiently. Distance uncertainty shifts luminosity estimates. Clumping uncertainty shifts opacity estimates. Both uncertainties alter inferred mass loss. The limit is a limit of resolution and inference. Scattering removes fine structure from the escaping signal. The inner boundary cannot be mapped directly when optical depth is high. The uncertainty is not large in every respect. Orders of magnitude can still be constrained. The direction of change can still be traced. The exact values can remain soft and model-dependent. Another small payoff follows from that softness. When direct measurements blur geometry becomes more reliable. The thickness of the limb and the curvature of ripples constrain how density declines with radius. The presence of a belt and a broad gradient constrains where scattering is strongest. Those constraints help separate a true luminosity change from a simple redistribution. The closing image returns to the cocoon with quieter light. The belt around the inner sphere thins and becomes less distinct. The outer fade grows dimmer and more transparent. The core glow looks sharper through a clearer path. The pseudo-photosphere retreats inward and reveals hotter layers. The wind continues outward in steady layers. Next, a rarer episode of loss comes forward. In that episode, the wind becomes a surge and the cocoon becomes the seed of a nebula shell. A giant eruption begins with a quiet thickening that looks almost like slow weather in light. The eruption is a sustained surge in mass loss that sends a dense wave outward and seeds a future nebula shell. The opening image holds near the star where the glow turns muffled. The bright core looks smaller behind a thicker veil. The veil grows smoother and more opaque. Its rim widens into a pale collar with a soft gradient. In that region, light behaves as if it must wade through fog. The first unlock is that an eruption is not a single blast. It is a change in the flow regime that lasts long enough to build structure. The wind becomes heavier. The outflow becomes denser close in. The pseudo-photosphere moves outward into cooler gas. Visible brightness can rise while the core remains hidden. The apparent star looks larger and whiter. That appearance is the signature of matter being lifted and carried away. A second unlock appears when the eruption wave meets the older wind. The older wind has layers from years of variability. The new wave catches those layers and compresses them. Compression makes a moving boundary that can later shine as a thin rim. The boundary becomes the birthplace of a shell. A calm visual anchor holds the early stages. A thickened envelope forms around the star like a smooth dome of pale light. Inside the dome, faint darker lanes appear as subtle gaps in density. The outer edge of the dome does not end sharply. It fades through a broad scattering gradient. At the same time, farther out, older arcs drift outward as faint, incomplete rings. The new dense wave grows and begins to overtake them. Where it overtakes, the arcs brighten into sharper threads. The threads trace a curved front. The front is not uniform. It is slightly thicker along an equatorial band and slightly thinner near the poles. The shape hints at rotation and latitude-dependent outflow. The eruption carries one primary timescale that feels slow and steady. A major outburst can persist for about 5 years, like a long storm season that does not break into a single lightning strike. Over those years, matter streams outward continuously. The flow is dense enough to build a substantial envelope. The envelope expands and cools. Cooling changes which atoms absorb and scatter. Opacity rises in some bands and falls in others. That changing opacity modulates how the eruption looks. It can brighten in visible light and then dim again. It can shift colour slightly without changing the deeper engine. The physical detail of layering remains clear in the gas. A thin bright rim forms at the outer boundary of the densest wave. Immediately behind it, a thicker zone appears more diffuse. This thicker zone contains mixed density pockets. Some pockets are dense clumps that lag behind the front. Some are rare gaps where light leaks more directly. The rim's brightness is enhanced because the path length through the compressed layer is longer at the edge. The limb looks like a curved blade of light. It has a sharper inner boundary and a softer outer fade. The sharper inner boundary marks where density jumps. The softer fade marks where compression relaxes into older wind. A new everyday analogy keeps the intuition gentle and unique. A slow pour of honey falls into a bowl of lighter syrup. The honey does not explode. It sinks and spreads. It forms a thick front where it meets the syrup. That front rolls outward as a rounded wave. It also traps thin sheets and folds as it moves. In the same way, the dense eruption flow meets a lighter wind and forms a rolling compression front. The rolling front gathers older layers into a single curved boundary. This explains why a shell can appear as a distinct rim even when the eruption is slow. The shell is the place where two flows meet and compress. A payoff follows from the honey image. The shell does not require a single instant of launch. It requires a contrast in density and speed. When the contrast is high, a thin boundary forms. When the contrast is low, the transition is broad and less visible. The eruption therefore builds visibility by building contrast. Another visual anchor appears as the front travels outward. A faint hollow region develops behind the rim. The hollow is not empty. It is lower density compared to the rim. Scattered light inside it looks dimmer and more uniform. The rim stands out as a curved edge that encloses a softly glowing interior. The shell begins to look like a lantern shade seen from the side. Its brightness is strongest along the edge. Its interior is faintly lit. The edge shows small ripples and wrinkles. Those wrinkles are instabilities where faster material slides past slower pockets. Each ripple becomes a seed for later clumps. A gentle scale shift follows one ripple from small to vast. The ripple begins as a local density enhancement near the star. It grows into a waviness along a rim that spans billions of kilometers. Over decades, the same waviness can become a filament in a nebula that stretches across a region where light takes years to cross. A limit of observation emerges from the same opacity that makes the eruption visually striking. When the wind is densest, the core is hidden behind scattering. The true mass loss rate cannot be weighed directly. It is inferred from brightness, color, and spectral features that form in an extended flow. Clumping can imitate higher mass loss by increasing emission in dense pockets. Porosity can imitate lower mass loss by letting light leak through gaps. Dust formation can dim and redden light and mimic cooling. Distance uncertainty can shift luminosity and therefore infer driving. The limit is a limit of inference and resolution. Fine structure in the inner flow is blurred into a smooth glow. Only large-scale geometry of the rim is robust. The rim curvature and thickness constrain the compression front. The exact mass and exact launch timing remain model-dependent. Another payoff follows from this limit. The shell is a record that survives even when the launch details fade. The shell preserves the contrast between eruption flow and older wind. It preserves the curvature that hints at anisotropy. It preserves the ripple pattern that hints at instability. Even without perfect numbers, the shell tells what kind of episode occurred. It tells whether the outflow was brief or sustained. It tells whether the wind was smooth or clumped. The closing image settles into calm expansion. The rim continues outward and becomes thinner relative to its radius. The interior remains softly lit by scattered light. The outer fade becomes more transparent as density drops with distance. The next step follows the shell into interaction. As the rim moves into older material, the boundary becomes a shock front. Compression grows more pronounced. The shell begins to brighten in narrow arcs where the collision is strongest. A shell becomes visible when a fast, dense flow meets a slower, older wind and draws a bright edge. The bright edge is a shock front that compresses gas into a thin rim and turns motion into structure. The opening image holds on the boundary itself. A curved arc of light traces a partial ring. The arc is sharper on its inner side. It fades outward through a softer gradient. The interior behind the arc looks dimmer and smoother. It resembles a calm cavity wrapped by a thin wall. In that region, light behaves as a marker of density, where gases compressed emission and scattering rise, where gases thin brightness falls. The first unlock is that the shell is not the ejected gas alone. The shell is the interface where new flow collides with old flow. The collision gathers material that was already present. It also slows the new flow. A second unlock follows from how shocks create a thin rim. A shock front is a thin region where flow changes abruptly. It compresses and heats gas. It also drives cooling that can make the rim denser and narrower. The rim becomes a folded boundary that can shine more than its surroundings. The geometry is the key. Compression piles matter into a sheet. A sheet seen edge-on looks brighter. A sheet seen face-on looks fainter. This explains why arcs and rings stand out. It also explains why the brightest parts often follow the limb. A calm visual anchor holds the collision. The dense wave from the eruption moves outward like a pale dome. Ahead of it lies older wind with faint ripples and arcs. Where the dome catches the ripples, a thin, bright filament appears. The filament curves around the star. It thickens in some directions and thins in others. Small corrugations run along it like gentle wrinkles in fabric. The wrinkles are not random. They grow where a lighter layer pushes against a heavier one. The rim becomes scalloped. Each scallop can become a knot later. Physical detail keeps the rim tangible. The rim has a brighter crest and a fainter skirt. The crest marks the densest compression. The skirt marks gas that is still being gathered. Behind the crest, the cavity shows faint striations that drift outward. Those striations are leftover flow lines. The cavity is not empty. It is simply lower density and more transparent. The third unlock explains why the shell can remain thin for a long time. Cooling behind the shock can be efficient in dense gas. As gas cools, it loses pressure support and collapses into a thinner layer. That collapse sharpens the rim. The rim then holds together like a compressed sheet. It stays coherent as it expands. Expansion makes the sheet thinner relative to its radius. The sheet can still remain visible because it contains much of the mass along the boundary. A single number frames the speed of the moving edge. A shock front can travel at about 200 kilometers per second, like crossing the distance from Earth to the Moon in about half an hour. This is slow compared to the fastest stellar winds. It is fast compared to the pace of most nebula evolution. Over a year, such a front moves far beyond the scale of a planetary system. Over centuries, it can define a nebula that spans regions where light takes years to cross. The scale shift is steady and calm. A microscopic change in ionization at the shock becomes a macroscopic ring in space. A new everyday analogy anchors the dynamics without repeating earlier images. It is like a slow snowplow pushing into soft snow. The plow gathers snow into a ridge. The ridge becomes higher and denser than the field. Behind the ridge, the road looks clearer. Ahead of it, the snow remains undisturbed. In the same way, the shock gathers gas into a ridge-like rim. Behind it, the cavity looks clearer. Ahead of it, older wind remains diffuse. The analogy also clarifies a payoff. The brightness does not require more light from the star. It requires more matter in the right geometry. The rim brightens because a thin sheet is packed with density. The sheet is seen through a long path length along the edge. Another visual anchor arrives as the rim grows and begins to deform. Two lobes appear instead of a perfect sphere. The rim pinches slightly near the middle. A waist forms where density is higher. The waist is thicker and brighter. Above and below, the lobes are fainter and more extended. The shape hints at a preference in the outflow. It also hints at the distribution of older wind. The shell becomes an hourglass silhouette with a glowing belt. The belt is a ring of compressed gas. It is not a solid ring. It is a curved sheet seen edge-on. The hourglass expands and the belt widens slowly. The belt also develops small knots that project inward as shadows. Those shadows appear where dense clumps scatter light away. A payoff follows from the shape. Geometry carries history. A spherical shell suggests a more uniform environment. A bipolar shell suggests an uneven environment or an uneven ejection. The rim is therefore a map of how matter was distributed before the eruption. It is also a map of how the eruption left the star. Another payoff arrives from the wrinkles along the rim. Wrinkles indicate instabilities. Instabilities seed clumps. Clumps can later cool and form dust in sheltered pockets. Dust changes scattering and dimming. The rim then evolves into a more textured structure. The collision thus sets the stage for later opacity changes. A limit of observation enters through projection and resolution. A ring on the sky can be a spherical shell seen edge-on. It can also be a bipolar structure viewed at a particular angle. A bright arc can be a full rim with only one limb visible. Distance affects inferred size. Viewing angle affects inferred thickness. The rim can look thinner if the instrument cannot resolve its width. The rim can look thicker if multiple layers overlap along the line of sight. Spectral lines can broaden for reasons beyond shock speed. Turbulence and multiple components can mimic a single strong shock. The limit is a limit of geometry inference. Without a full three-dimensional view, models must assume symmetry. Those assumptions can be wrong in detail. Yet some conclusions remain stable. Compression is required for sharp rims. Interaction between flows is required for strong contrast. The shell therefore still testifies to collision even when angles are uncertain. The closing image settles the rim into a calmer outward drift. The bright filament continues expanding and the cavity grows larger. The scallops along the crest stretch and become longer filaments. The waist remains a thicker band that slowly thins as it expands. Next, the shell's shape and thickness begin to reflect rotation and layered winds more clearly. The story moves from a single front to an evolving sculpted nebula. A nebula shell rarely stays perfectly round once expansion begins to feel the star's rotation and layered winds. The shell's shape emerges from uneven density and speed that pinch the flow into lobes and belts. The opening image holds on the shell at mid-expansion. A bright rim traces an hourglass outline. A thinner glow fills the interior. A thicker band wraps the middle like a luminous belt. The belt is brighter where the line of sight crosses more compressed gas. It fades into a softer skirt away from the waist. At this distance, light behaves as a brush that paints density onto the sky. The first unlock is that bipolar shape can form without a violent directional jet. It can arise from a wind that is denser in one latitude band. It can also arise from older material that is not evenly distributed. When the eruption flow hits a denser equatorial region, it slows sooner. It piles up into a thicker ridge. When it expands into lower density polar regions, it travels farther and faster. The result is a pinched waist with extended lobes. A second unlock follows from the shell's thickness. A thin sheet becomes bright at its limb. A thicker sheet becomes bright across a broader zone. The waist often looks thicker because compression lasts longer there. The lobes often look thinner because material spreads as it expands. This difference in thickness produces different gradients of brightness. The waist shows a steep inner edge and a broader outer fade. The lobes show a narrower rim and a fainter interior. Physical detail keeps the structure tangible. The rim is scalloped with small ripples. Each ripple is a wave in the compressed sheet. Some ripples curl into finger-like protrusions that point inward. Those fingers cast faint shadows into the cavity by scattering light away. The cavity remains filled with low-density gas. It is smoother and more uniform in brightness. The waist region shows knots that are denser and cooler. The knots appear as small bright beads along the belt. A calm visual anchor holds the full shape. The shell looks like two translucent bowls joined at their rims. Between them the belt glows like a ring of pearl. The belt is not separate from the bowls. It is the same sheet seen edge-on. Thin wisps extend outward from the lobes. The wisps are stretched layers that have cooled and thinned. They fade into darkness without a hard end. A single number frames the role of rotation. A massive star can rotate once every few days like a slow spinning lantern that keeps the same glow. That rotation does not throw matter off by itself in most cases. It does change the effective gravity with latitude. It also shapes how the wind is launched over long time. The equator can be slightly more favourable for dense outflow. The poles can be more favourable for faster flow. Over years, that difference sets up an asymmetry in the ambient wind. When an eruption arrives, it expands into that asymmetry. The rotation period becomes a small clock that prints a large geometry. The scale shift is gentle. A difference in effective gravity across a photosphere becomes a bipolar shell spanning billions of kilometres. Over centuries, the bipolar outline can remain recognisable as it drifts into interstellar space. A new everyday analogy anchors the pinched shape without repeating earlier ones. It is like smoke rising through a narrow doorway. Where the doorway is narrowest, smoke compresses into a thicker band. Above and below, it spreads into wider plumes. The smoke does not need a fan to make two lobes. The constraint of the doorway and the surrounding air shapes the flow. In the same way, a denser equatorial zone acts like a constraint. It narrows the expansion and forces material into a belt. The lobes form where resistance is lower. A payoff follows from this analogy. The shape is a map of where the environment is thick and where it is thin. It also reveals where the eruption flow loses momentum. Another visual anchor appears along the belt. The belt shows a double rim. Two close arcs run parallel with a thin dim lane between them. The dim lane marks a small cavity inside the compressed sheet. It forms when multiple waves catch up and stack. The double rim indicates layered shocks rather than one single front. It also indicates time structure in the eruption. A steadier eruption produces a smoother belt. A more variable eruption produces multiple arcs. This offers a quiet payoff. The shell can record timing by layering its own rim. The next checkpoint deepens the geometry into texture. Instabilities grow faster where the shell is decelerating. Deceleration is strongest where dense material slows the rim. The waist therefore becomes a nursery for knots. Knots cool and contract. Contraction increases density and sharpens edges. The lobes remain more diffuse because deceleration is weaker. The rim there is less corrugated. The difference in texture becomes another map. Texture traces where the shell is being braked. A limit of observation appears when shape is inferred from a single viewpoint. A bipolar shell can look like a ring if viewed along its axis. A near spherical shell can look bipolar if brightness is uneven. Projection effects can hide one lobe behind another. Resolution limits can blend a double rim into one. Distance uncertainty can change inferred size and age. Spectral line splitting can be interpreted as expansion velocity. Multiple components along the line of sight can mimic a faster flow. Models often assume symmetry to reduce ambiguity. Real shells can be patchy and incomplete. The limit is a limit of three-dimensional reconstruction. Without full mapping of velocity and density, some shapes remain degenerate, yet some conclusions remain stable. A thick waist implies strong equatorial compression. A thin lobe implies freer expansion. A double rim implies layered episodes or shocks. The shell therefore still carries reliable clues even when the view is incomplete. The closing image keeps the hourglass calm and steady. The belt continues outward and thins as radius grows. The lobes extend farther and become fainter at the tips. The double rim softens as the arc spread. Next, the shell's chemistry and dust begin to matter more. Dense knots cool enough to form grains. Scattering changes again and the nebula shifts from pure gas glow to a mix of light and dust. A nebula shell changes character when cold pockets inside it begin to grow solid grains. Dust forms in dense knots and turns a gas shell into a soft lantern of scattered light. The opening image holds on the waist region where clumps are thickest. Small bright beads sit along a curved rim. Around each bead a faint halo appears. The halo is not a separate object, it is light scattered by tiny grains in a thin envelope. The rim still shows a sharp crest. The crest fades outward through a smooth gradient. The interior looks dimmer as if the shell holds a gentle shadow. At this distance, light behaves as both illumination and probe. It brightens dust by scattering. It also dims the background by absorption. The first unlock is that dust does not require the whole shell to cool at once. It forms locally where density is high and cooling is efficient. After a shock compresses gas, the gas can radiate energy and cool. Cooling lowers thermal pressure. Lower pressure allows further compression. Compression increases density again. In the densest pockets, molecules can survive longer. Grains can then condense on suitable seeds. Dust is solid particles made of heavy elements. The particles are tiny but numerous. They alter how light passes through the shell. The second unlock follows from a simple difference between gas glow and dust glow. Gas glow often traces hot or energized regions. Dust glow traces where grains intercept light. Dust can therefore highlight cool, dense knots that gas emission might not emphasize. Dust also changes the shell's silhouette. The edge can become softer in some bands because scattering spreads light. The interior can become darker in other bands because absorption removes light. A calm visual anchor holds the beginning of grain growth. The rim looks like a strand of pearls. Each pearl is a dense knot. Between pearls, the rim is thinner and fainter. Around the pearls, a faint veil extends inward like short wisps. Those wisps are not jets. They are shadowed lanes where dust absorbs and scatters. The shell becomes textured. The texture is not random. It follows the places where compression and cooling are strongest. Physical detail keeps the grains connected to structure. The knots have sharper inner edges and softer outer skirts. The inner edges face the star and receive stronger radiation. The outer skirts face colder space and cool more easily. The difference creates a gradient in grain temperature. The knots can also develop layered skins. An inner skin is warmer and less dusty. An outer skin is cooler and dustier. The shell then contains microlayers inside a macro rim. The third unlock explains why dust can persist even when the environment is harsh. Radiation can destroy fragile molecules. It can also heat grains. Dense clumps provide shielding. Shielding is simply having enough material to absorb and scatter photons before they reach the center. The outer layers of a knot can protect the interior. The interior remains cooler. It becomes a quiet refuge where grains survive. The same shielding creates a visible effect. A shadowed lane appears behind a knot. The lane points away from the star. It is a cone of reduced brightness where light is blocked and redirected. These shadows are geometric clues. They reveal which side faces the star. They also reveal how thick the knot is. A single number frames the grain scale without becoming technical. Typical grains can be about 1/10 of a micrometer across like smoke particles, too small to see individually. This size is small enough that huge numbers are needed to matter. Yet the collective effect is strong. Many tiny grains can change a whole nebula's appearance. The scale shift is gentle. A particle smaller than a bacterium can sculpt brightness across a shell that spans billions of kilometers. Over centuries, dust can drift outward and mix into surrounding clouds. Over longer spans, those grains become ingredients for later cold clouds. The everyday analogy stays unique and calm. It is like frost forming on a window pane at night. Frost does not coat the whole glass evenly. It begins at tiny imperfections. It grows into branching patches. The patches scatter light and soften outlines seen through the glass. In a shell, dust begins in dense knots. It grows into patchy veils. It softens the outline of the rim in some directions. It darkens the interior in others. The analogy also delivers a payoff. Dust makes the shell easier to see in reflected light even when gas emission fades. The shell becomes a reflector as well as an emitter. Another visual anchor appears as dust accumulates. The waste belt develops a mottled pattern. Bright patches sit beside dim patches. The bright patches are where scattering is strong. The dim patches are where absorption or shadowing is strong. Along the lobes, dust is sparser. The lobes remain smoother. This contrast emphasizes the bipolar shape. The shell looks like a double bowl with a speckled belt. The speckles drift outward with the flow. Some speckles elongate into short filaments. Filaments appear where knots are stretched by expansion. The filaments remain aligned with the rim. They trace the direction of motion. A payoff follows from the speckles. Dust acts like a tracer of density history. Where dust is abundant, compression and cooling must have been strong. Where dust is scarce, the flow must have remained hotter or thinner. Dust therefore reveals which parts of the shell are more decelerated. It also reveals where instabilities produced long-lived clumps. Another payoff arrives from how dust affects inferred mass. If dust absorbs some light, the star can appear dimmer than it truly is in some bands. If dust scatters light, the shell can appear brighter than gas emission alone would predict. Interpreting brightness then requires separating direct light from scattered light. It also requires accounting for grain size distribution. A limit of observation enters here. Grain properties cannot be measured directly in most cases. They are inferred from how brightness changes with wavelength. Different mixtures of grain sizes and compositions can produce similar color changes. Clumping can hide dust in optically thick knots. Those knots can appear dark even when dust is abundant inside. The limit is a limit of degeneracy in models. Many combinations of dust amount and grain size can match the same broad spectrum. Resolution also matters. A bright patch can hide many smaller knots within it. A dim lane can be a true cavity or a shadow cast by a nearby clump. Without full mapping, inference remains partly indirect. Yet some conclusions remain robust. Dust must be present when scattering halos and shadow cones appear. Dense knots must exist when sharp beads persist along the rim. The shell therefore still carries reliable evidence of dust formation even when details vary. The closing image softens the rim further. The pearl strand becomes slightly more diffuse as grains spread into the skirts. The interior shadow deepens in places where absorption increases. The outer fade becomes warmer and smoother as scattered light fills it. Next, the shell's chemistry comes forward. The gas and dust carry fingerprints of deep layers. Those fingerprints reveal what the star has processed and what it has released into its surroundings. A nebula shell quietly carries a chemical memory of what the star's interior has been turning into new material. The shell's gas often shows enrichment from processed layers that reach the surface during heavy mass loss. The opening image holds on the rim where light is strongest. The rim shows a thin, bright crest and a broader, faint skirt. Along the crest, knots appear as small beads. Between beads, the rim becomes a smoother filament. The interior remains softly lit and slightly shadowed. At this distance, light behaves as a sorter. Different wavelengths emphasize different ions and different zones. The first unlock is that composition can be inferred from which lines strengthen and where they appear. The gas in the shell is not a perfect sample of the star's whole mass. It is a sample of outer layers that have been peeled away. When a luminous blue variable loses mass, strongly deeper material can be exposed. That material has been altered by nuclear burning in the core and by mixing in the envelope. Mixing is the transport of material between layers. It can be driven by rotation and by turbulence in unstable zones. The result is that some elements become more abundant at the surface. Helium and nitrogen often rise in relative strength. Carbon and oxygen can appear reduced in some cases. The shell therefore becomes a slow signature of internal processing. The second unlock follows from how the shell separates into zones. The rim is compressed and often cooler. The interior is lower density and more ionized. A thin transition layer sits between them where ionization changes rapidly. That transition layer appears as a gradient in brightness and color. It can also appear as a shift in which lines dominate. The same gas composition can look different depending on ionization state. Ionization depends on radiation and on density. Dense knots can remain less ionized because they recombine faster. Diffuse regions stay more ionized because photons penetrate deeper. The shell therefore displays chemical clues in a layered way. The rim may highlight lower ionization lines. The interior may highlight higher ionization lines. This layered structure is a physical detail that keeps the chemistry grounded. A calm visual anchor holds the shell as a stained glass dome. The rim is a brighter leading edge like a curved window frame. Within the frame, patches of different glow appear. Some patches sit on knots and look warmer and thicker. Some patches lie in diffuse lanes and look cooler and smoother. The frame contains thin striations that curve along the flow. Each striation marks a change in density and ionization. The stained glass analogy is not about colour alone, it is about selective transmission. Some panes let certain light through, some panes block it. In a shell, different regions transmit and emit differently because composition and ionization vary. A payoff follows from this image. The shell is not chemically uniform. It is a mosaic that preserves how material was lifted and compressed. The third unlock connects the shell's chemistry to the star's past and future. Nitrogen enrichment hints at processed material brought upward. It suggests that the star has mixed interior products into its envelope. That mixing often accompanies strong mass loss and near-threshold luminosity. It also suggests that the star is moving toward a more stripped state. Stripping removes the hydrogen-rich envelope. A stripped star later produces a faster, hotter wind. That future wind can collide with older, slower material and further shape the nebula. The shell therefore sits between phases. It records what has been removed and hints at what remains. One primary number frames the scale of the shell's chemical reservoir. A luminous shell can contain about 1 sun mass of gas, like the entire mass of the sun spread into a thin, drifting sheet. This mass is not concentrated. It is dispersed across a huge surface area. The same mass becomes nearly invisible if spread thin enough. It becomes visible when compressed into rims and knots. The number also brings a scale shift. A star's interior rearranges nuclei in microscopic reactions. Those microscopic changes become a macroscopic nebula with mass comparable to a star. Over centuries, that mass continues outward. Over longer spans, it mixes into surrounding clouds and becomes part of new star-forming material. The everyday analogy stays unique and quiet. It is like a tea bag steeping in water and then being lifted out. The water carries a concentrated imprint near the bag at first. Later it becomes more uniform as it stirs and diffuses. In a shell, the densest knots are like local concentrated regions. The diffuse interior is like the stirred water. The imprint is not only colour, it is composition and ionization. The analogy also delivers a payoff. Mixing in the nebula does not erase the rim quickly. Compression keeps contrasts alive. Another visual anchor appears along the rim where composition meets dust. Some knots show a brighter halo from scattering. Behind them, shadowed cones extend inward. These cones mark where dust and dense gas absorb and scatter. The cones help locate the densest zones. Those zones are also where chemistry can look different. Dense zones can harbour molecules and lower ionization species. Diffuse zones cannot. The shell therefore offers a layered chemistry map. The map is readable through patterns of brightness, rim thickness, and shadowing. A payoff follows from this layered map. Even without direct access to the star, the shell can reveal whether deeper processed layers have been exposed. It can also reveal whether mass loss was episodic. Multiple rims and multiple chemical zones suggest multiple episodes. A single smooth rim suggests a more coherent event. Chemistry therefore supports the structural story told by arcs and belts. A limit of observation enters with the inference of abundances. Line strengths depend on density and temperature. They also depend on ionization and on dust extinction. A region can appear nitrogen-rich if ionization favours nitrogen lines. A region can appear carbon-poor if carbon lines form in a different zone. Clumping can boost emission because emission scales with density squared in many cases. That effect can bias inferred abundances toward dense knots. Distance and geometry uncertainties also matter. Overlapping layers along the line of sight can mix signals from different zones. Resolution can blend knots and diffuse gas into 1 pixel and hide gradients. The limit is a limit of disentangling physical conditions. Composition cannot be read without modelling temperature and ionization. Those models carry degeneracies, yet some conclusions remain stable in broad strokes. Enrichment patterns across many lines and many zones point to processed material. Consistent rim dominance in low ionization species points to dense cooling compression. The shell thus still carries a reliable chemical memory, even when exact ratios vary. The closing image returns to the stained glass dome as it drifts outward. The rim remains the brightest frame, The interior mosaic remains faint and soft. The shadow cones remain aligned away from the star. Next, the shell's multiple episodes come forward more clearly. Concentric arcs and nested rims suggest repeated surges. The story moves from one shell to a sequence of shells that mark a longer rhythm. A luminous blue variable can leave more than one shell, and the shells can sit like nested rings in slow expansion. Multiple episodes of mass loss stack into layers that preserve timing as geometry. The opening image holds on a wide field around the star. Two faint arcs appear outside the bright main rim. Each arc is thinner and dimmer than the main shell. Each arc follows the same general curvature. The arcs are separated by darker lanes where density is lower. The main rim remains the brightest crest. It has a sharp inner edge and a broader outward fade. In that region, light behaves as a time marker. It highlights where matter has been compressed and where it has thinned. The first unlock is that repeated shells do not require identical eruptions. A steady wind can lay down one layer. A heavier surge can lay down another. A later surge can catch the earlier layer and brighten it into a rim. What looks like a discrete shell can be an old density wave made visible by later interaction. This resolves a quiet question. Multiple rings can come from a sequence of changes rather than a sequence of explosions. The second unlock follows from the spacing between the rings. Spacing is a clock when the expansion speed is known in order of magnitude. If a rim moves outward at roughly the same pace over time, then distance between rims reflects time between episodes. A single number frames that spacing scale. A typical ring separation can be about 1 light year, like the distance light crosses in a year. That is also a vast region compared to any planetary orbit. Such spacing implies long intervals between major episodes. It implies decades to centuries between strong surges in many cases. The scale shift is gentle. A brief change in the star's outer wind can later appear as a ring separated by a distance that light takes a year to traverse. Over thousands of years, multiple rings can drift far from the star and merge into surrounding clouds. Calm visual anchor holds the nested geometry. The main shell appears as a bright ellipse with a thick waist. Outside it, a thinner ellipse mirrors the shape. Outside that, a faint arc appears only on one side, like a partial halo. The partial halo is not incomplete by accident. It is incomplete because density is uneven. It is also incomplete because viewing angle and projection emphasize some limbs more than others. Along the brighter limbs, the rim looks like a thin thread. Along the fainter limbs, it fades into a broad gradient. The lanes between rings are darker. They are not empty. They are lower density zones where scattering and emission are weaker. Physical detail keeps the rings tied to flow. The outer arcs have smoother surfaces. The inner rim has knots and scallops. This difference suggests that older shells have had more time to smooth and spread. It also suggests that the inner shell is still actively being shaped by interaction. The third unlock explains how stacking naturally occurs. Each episode leaves material at a particular radius. Later episodes expand into that material. Where they collide, compression builds a new rim. Where they expand into lower density, they remain diffuse. Over time, shells can overtake and merge. The collision of shells can create a brightened interface layer. That interface can resemble a new ring. The process is like a slow traffic pattern in space. Faster flow catches slower flow. A boundary forms where speeds equalize. That boundary becomes a thin sheet. The thin sheet becomes a visible rim. A new everyday analogy anchors the layering without repeating earlier ones. It is like ripples from repeated drops falling into a still pond. Each drop creates a ring that expands outward. When a later ring catches an earlier ring, the water surface briefly forms a stronger ridge. The ridge is not a new drop, it is an overlap of waves. In a nebula, shells are not water waves. They are matter, yet the overlap idea remains useful. Later surges can reinforce earlier density structures. Reinforcement makes a rim easier to see. The analogy also delivers a payoff. Visibility can rise when shells interact, even if the star is no longer in an active phase. Another visual anchor appears at the interface of two shells. A thin, bright filament runs parallel to the main rim but slightly outside it. Between the filament and the main rim lies a narrow, dim lane. The lane is a small cavity where density has been swept away. The filament is the compressed boundary where two flows meet. It is sharper than the older outer arcs because it is newly formed. The filament also shows faint, regular corrugations. The corrugations are small instabilities growing as the boundary decelerates. Each corrugation can seed a knot. Each knot can later become a dust-rich bead. A payoff follows from the corrugations. Repetition in shells does not mean repetition in detail. Each interaction writes new texture onto an older ring. The ring becomes a palimpsest of episodes. Another payoff arrives from the asymmetry of outer arcs. A partial halo suggests that the environment is not uniform. One side may have denser ambient material. There the shell slows and brightens. The other side may expand more freely and fade. This difference means the star's history is written not only by internal episodes. It is also written by external surroundings. A shell is shaped by what it meets. The star's wind does not expand into a perfect vacuum. It expands into previous wind and into local interstellar material. The nested pattern therefore encodes both internal and external structure. A limit of observation enters through the same nested complexity. Distinguishing separate shells from a single shell with multiple filaments is difficult. Projection can stack unrelated layers along the line of sight. A partial ring can be part of a bipolar lobe seen at an angle. A full ring can be a limb-brightened spherical sheet. Distance uncertainty changes physical size and inferred timing. Velocity measurements can vary with position. A faster region in a lobe can mimic a younger shell. A slower region in a dense waste can mimic an older shell. The limit is a limit of three-dimensional reconstruction and of model assumptions. Without complete velocity mapping across the whole nebula shell, counting can be ambiguous. Yet some conclusions remain stable. Multiple distinct rims with distinct lanes imply real layering and density. Sharp interface filaments imply collisions between flows. Outer smoother arcs imply older material that has expanded and diluted. The closing image widens and calms the scene. The main shell continues outwards, and its knots slowly stretch into filaments. The interface filament softens as compression relaxes. The outer arcs remain faint and broad. Next, the story steps farther back in time. The star's evolution through burning spheres sets why such episodes happen at all. The shell becomes a surface record of a deeper internal clock. A luminous blue variable sits near a balance point where small internal changes can reshape the outer layers. The star's evolution sets the conditions that make repeated surges and shells possible. The opening image holds close to the star. The surrounding wind forms a pale envelope with a smooth brightness gradient. Inside the gradient, faint arcs drift outward like soft rings of haze. The arcs are subtle but persistent. They mark older density changes. The inner glow looks steady but veiled. Its edge is not sharp. It is a soft boundary where scattering fades. In that region, light behaves as a messenger that has travelled through layers. The first unlock is that the outer envelope can respond strongly while the core changes slowly. The core advances through burning stages deep inside. The energy generation remains enormous but regulated. The envelope by contrast can become unstable. It can inflate and contract. It can change opacity as ionization shifts. Those opacity changes alter how radiation pushes outward. When opacity rises, radiation couples more strongly to the gas. When opacity falls, radiation slips through more easily. The wind can thicken or thin in response. This explains how the star can vary in apparent temperature and radius without a dramatic change in core output. The second unlock follows from a boundary in the outer layers. A region of partial ionization can act like a valve for energy transport. Partial ionization means electrons are not fully stripped. In that state, adding heat goes into ionizing atoms rather than raising temperature. That delays temperature rise and changes pressure response. It can promote pulsation and envelope inflation. The effect is not a simple on-off switch. It is a soft zone that shifts with density and radiation. It can move inward or outward. As it moves, the apparent surface can shift. The wind can respond with a denser phase. A denser phase can later be recorded as a ring. A calm visual anchor holds this internal to external connection. Inside the envelope, a faint layered band appears like a translucent stratified cloud. One layer is slightly brighter and thicker, another is thinner and more diffuse. The layers drift outward and separate. Each layer has a sharper inner edge and a softer outer fade. The sharper edge marks a change in density, the softer fade marks gradual dilution. The star's outer regions thus look like a slow-breathing atmosphere that leaves behind thin sheets. Physical detail keeps the layering grounded. The sheets are not flat, they are curved around the star, they are slightly thicker near the equator, they are slightly thinner toward the poles, small ripples run along them. Those ripples are waves from pulsation and from turbulence. Each ripple can later seed a clump. The third unlock connects evolution to timescales that feel both long and intimate. The star's core evolves over hundreds of thousands of years. The envelope can change on years to decades. The nebula records the envelope timescale, not the core timescale, yet the envelope changes are guided by where the star is in its life. As mass loss removes the hydrogen-rich outer layers, the star becomes more compact and hotter. The wind becomes faster and more ionizing. That shift changes how new outflows collide with older ones. It also changes how shells are lit and shaped. The shell therefore marks a transitional corridor in stellar evolution. One primary number frames the mass scale that matters for this transition. Removing about 10 sun masses, like losing 10 copies of the sun's mass into space, can move a massive star toward a more stripped state. This number is approximate and depends on the star. It remains useful as order of magnitude. The scale shift is gentle. Nuclear reactions in a core smaller than a planet can ultimately shed mass comparable to many suns into a nebula, larger than a solar system by far. Over thousands of years, that lost mass drifts outward and mixes into the surrounding medium. Over much longer spans, it becomes part of future clouds. The everyday analogy stays unique and calm. It is like peeling layers from an onion. Each layer removed reveals a slightly different texture underneath. The onion does not change its center quickly. The surface changes with each peel. In a star mass loss peels away outer layers. Each peeling can expose material that has been mixed from deeper zones. Each peeling changes how the wind is launched. The analogy also delivers a payoff. The nebula is the pile of peeled layers carried outward. Each shell is one layer or a set of layers. Another visual anchor appears farther out where multiple shells overlap. The shells appear as nested arcs with different thicknesses. The inner arc is sharp and knotted. The next arc is smoother and broader. The outer arc is faint and almost uniform. The spacing between them is not perfectly even. Some arcs are closer together, some are farther apart. This irregular spacing suggests that episodes are not strictly periodic. They occur when conditions cross a threshold. That threshold can be related to opacity and to envelope instability. A payoff follows from irregular spacing. The star's variability is a response to internal conditions and not a simple clock. Yet the shells still carry a rough rhythm. The shells show that major episodes occur separated by decades or centuries in many cases. The shells therefore bridge human-like timescales and deep stellar timescales without requiring human reference. Another payoff arrives from the link between stripping and future wind. A more stripped star can later blow a faster wind that shapes older shells into sharper rims. That faster wind can also erode and fragment older rings. The nebula becomes more filamentary over time. The earlier smooth sheets become later torn curtains. The shell's present shape is thus a snapshot within an evolving sequence. A limit of observation enters through the difficulty of seeing the internal causes. The core cannot be observed directly. Envelope structure is inferred from spectra and variability. Different models can reproduce similar light curves. Rotation and magnetic fields can alter mixing but are hard to measure in detail. Binarity can also alter mass loss but can be hidden by dust and glare. The limit is a limit of indirect inference and of degeneracy. Many internal configurations can yield similar external signatures. Yet the shell provides constraints. Multiple shells require multiple density enhancements. Strong enrichment requires exposure or mixing of processed material. Bipolar shapes require anisotropy in wind or environment. These constraints narrow the space of models. They do not select one unique story. They do support a general picture of an unstable envelope near a critical balance. The closing image returns to the layered cloud around the star. The brighter layer drifts outward and thins. The next layer follows behind it. Farther out, older layers continue fading into the background. Next, attention shifts to the broader environment. The surrounding medium shapes how far shells travel and how long they remain visible. The star's record becomes part of a larger cloud landscape. A nebula shell rarely expands into perfect emptiness, and its brightest edge often forms where it meets unseen surrounding gas. The shell's long life is set by pressure and density in the region it enters. The opening image holds on one side of the nebula, where the rim looks sharper. The rim there is a bright crescent with a narrow crest. Just outside the crest, a faint haze appears like a soft apron. On the opposite side, the rim is wider and dimmer. It fades through a gentle gradient. In that region, light behaves as a tracer of resistance. Where the shell meets denser material, compression strengthens the glow. Where it meets thinner material, the glow spreads and weakens. The first unlock is that asymmetry can come from the environment as much as from the star. A shell that begins nearly symmetric can become lopsided when it reaches a density boundary. The boundary can be a drift of older wind. It can also be a nearby interstellar cloud edge. The boundary does not need to be sharp. Even a slow change in density across space can sculpt one side into a bright arc. The opposite side remains diffuse. A second unlock follows from the crest's thinness. A thin, bright limb often means the emitting layer is a compressed sheet. Compression increases density. Higher density makes cooling more efficient. Cooling allows the sheet to become thinner. The sheet then brightens at the limb because the line of sight crosses more material. Physical detail holds the sheet in view. The crescent crest shows a scalloped edge. The scallops are small ripples that run along the arc. Behind the crest, the interior looks slightly darker. The darkness is not empty space. It is lower density gas that emits less. It also contains faint veils of dust that scatter light away. Another visual anchor enters slowly. Ahead of the crescent, a faint curved front appears. It sits slightly outside the main rim and bows outward. It is like a second, softer arc that leads the way. Between the two arcs lies a thin, dim lane. The lane marks a region where gas has been swept and rarefied. The leading arc marks a gentle shock in the surrounding medium. The trailing arc marks the shell's own compressed layer. This pairing is a quiet payoff. Two arcs can separate the place where the shell meets the environment from the place where the shell's material piles up. The shell becomes a moving boundary system rather than a single wall. One primary number frames the balance between shell and surroundings. A typical surrounding density can be about one atom in each cubic centimetre, like one grain of sand spread through a box the size of a small room. This number sounds sparse, yet it matters at large scales. Over a region as wide as a nebula, even sparse gas adds up. As the shell sweeps it up, the added mass slows the expansion. The scale shift is gentle. A density that seems nearly nothing at small scales becomes a significant break across distances larger than a solar system by far. Over thousands of years, this breaking decides whether a shell stays coherent or dissolves into filaments. A new everyday analogy anchors the interaction without repeating earlier ones. It is like a moving fog bank sliding into a hillside of denser air. Where the hillside air is thicker, the fog edge sharpens and brightens in the sunlight. Where the air is thinner, the edge remains soft and spread out. The fog does not need to change at its source. The landscape changes the outline. In a nebula, the landscape is density and pressure. The analogy delivers another payoff. The brightest rim does not always mark the most material ejected. It can mark the strongest encounter with surrounding gas. Another visual anchor appears along the bright crescent. Short curls form on the crest's outer edge. The curls roll back like small breaking waves. Each curl is a shear layer where faster flow slides past slower gas. The curl's inner side is brighter, the outer side is fainter. This contrast shows where compression is strongest. It also shows where mixing begins. Mixing here is not gentle diffusion alone, it is the physical stirring of gas by instabilities. As curls grow, the crest becomes ragged. Raggedness is a clue. It means the shell is transferring momentum to the environment. It also means the shell is being seeded with fragments that can drift away. A payoff follows. The environment does not only shape the shell, it gradually absorbs it. A third unlock builds from pressure balance. As the shell expands, its internal pressure drops. Surrounding pressure stays more constant across time. Eventually, the two pressures become comparable. At that point, expansion slows and the shell stops behaving like a freely moving wave. It becomes a stalled layer that drifts and mixes. The rim then broadens, its sharp crest softens. The dim lane between paired arcs can fill in as turbulence stirs material back. The nebula's outline becomes less geometric and more cloud-like. Physical detail keeps this transition tangible. The broadening rim develops a thicker skirt. The skirt shows faint striations aligned with the arc. Each striation is a density layer stretched by flow. The interior shadow becomes patchier. Some patches darken where dust is concentrated. Some patches brighten where scattered light fills cavities. The crescent remains recognizable, yet it loses its crispness. Another payoff appears in the timing of this softening. A shell that remains crisp likely expands into a low-pressure region. A shell that becomes ragged early likely meets denser surroundings sooner. This ties environment to visibility time. The nebula is brightest when compression and illumination overlap. It dims when density spreads and when radiation weakens with distance. A limit of observation enters here. The surrounding medium is difficult to measure directly. Its density can be inferred from how fast the shell slows and from emission brightness. Those inferences depend on distance and geometry. Projection can exaggerate a crescent by limb brightening. A true density wall can be confused with a viewing angle effect. Cold neutral gas can remain invisible in many bands. Dust can hide mass inside dark patches. Resolution can blur paired arcs into one. The limit is a limit of reconstructing three-dimensional environment from two-dimensional brightness. Models can fit the same arc with different ambient densities if shell thickness and clumping differ. Yet some conclusions remain stable. A bright sharp crescent with a leading faint front strongly suggests interaction with external material. Ragged curls strongly suggest shear and mixing. Paired arcs strongly suggest a swept zone between shock and shell. The closing image holds the nebula from farther away. One side shows a bright crescent and a faint bow. The other side fades into a wider halo. Small curls along the crest continue to grow and then soften. The shell slowly becomes part of the surrounding cloud field. Next, attention shifts to the longest consequences. The shells and their dust enrich the larger medium and alter how later clouds cool and fragment. The nebula's slow motion record becomes a quiet contribution to the next cycle of star-forming material. A nebula shell around a luminous blue variable is not only a record of loss, it is also a delivery of new material into the wider medium. The opening image holds on a faint outer halo beyond the bright rim. The halo looks like a thin veil with streaks and patches. Some streaks are pale and smooth, some patches are darker and more granular. Along one edge, the halo shows a subtle color gradient. One side leans toward softer blue, the other leans toward warmer tones. This gradient is not a decoration. It hints at different kinds of emission and different grain populations. In that region, light behaves as both illumination and filter. Dust scatters shorter wavelengths more strongly. Gas lines brighten where density and radiation meet. The first unlock is that dust can form and survive inside these shells. Dust here is solid grains in a harsh environment. It seems unlikely at first. Radiation is intense, shocks occur, yet dense clumps and cooled layers create pockets where grains can grow. When grains form, they change what the shell does next. They absorb and re-radiate energy. They help gas cool by offering surfaces. They also carry elements into the medium. A second unlock follows from chemistry and layering. Material in the shell is not always identical to the surrounding medium. It can be enriched by processed elements that have been mixed outward. It can also be structured into dense clumps and thin sheets. Clumps protect molecules and grains. Sheets provide large surfaces for cooling. Together they turn a shell into a patchy factory rather than a smooth bubble. The physical detail holds on the clumps. Along the rim's interior, small knots appear like beads on a thread. Each knot casts a slight shadow behind it in mission. The shadow is a wedge of lower brightness. It forms because the knot blocks radiation, and because its wake is rarefied. Between knots, the rim is smoother and brighter. This alternating pattern is a slow rhythm. It is also a map of density. A payoff arrives from the shadows. Shadows show that illumination direction matters. They show that the shell is not uniformly lit. The side facing the star is brighter. The lee side is cooler and more sheltered. That sheltered side is where dust can persist longer. Another visual anchor enters farther out where dust reveals itself indirectly. The halo shows faint lanes that look like smoke trails. The lanes curve and taper. They do not match the sharp gas rim. They float beyond it like a second component. The lanes are dust-rich filaments that have decoupled slightly from the gas flow. They drift with pressure and turbulence. They also respond to radiation forces. A payoff follows. Dust can trace older structures that a gas emission no longer highlights. The shell can therefore outlive its own brightness by leaving a dusty outline. One primary number frames the cooling reach of dust. Grains warm to about 100 degrees like a gentle oven. Set low radiate strongly in the infrared. This temperature is not hot in everyday terms. In space it is warm. It marks a regime where dust glows, rather than only blocks. It means dust can be visible as emission, even when gas lines fade. The scale shift is gentle. A grain smaller than a speck of smoke can in a vast shell influence how energy moves across distances larger than a solar system by far. Over tens of thousands of years, dust grains can travel outward and mix into broader clouds. Over much longer spans, they can become part of future dense regions. A new everyday analogy anchors this contribution without repeating earlier ones. It is like adding fine flour to a large pot of soup. The flour is not the main ingredient by mass. It changes the soup's texture and how heat spreads. It also carries flavors that diffuse through the whole pot. In a nebula, dust is the fine flour. It changes cooling and opacity. It carries elements. It seeds later chemistry. The analogy delivers another payoff. Even a small fraction of solids can shift the behavior of a much larger gas mass. Another checkpoint moves to how enrichment becomes a larger scale effect. As shells slow, they merge with surrounding material. Their clumps are stretched into filaments by shear. Their sheets fragment into arcs. Mixing begins at boundaries where turbulence grows. Each boundary is a place where new composition meets old composition. Over time, differences blur. Yet the mixture is not uniform at first. It appears as streaks and gradients. In the halo, pale streaks represent regions where gas is more ionized. Dark lanes represent dust-rich regions where radiation is muted. The rim's knots become small sources of shadowed wakes. A payoff follows from the wake pattern. Wakes extend in consistent directions, implying a coherent flow field. That flow field can be set by expansion and by ambient motion. It can also be influenced by large-scale pressure gradients in the surrounding medium. The nebula therefore becomes a tracer of the local cloud dynamics. Another visual anchor appears as a broad bow-shaped arc in the outer halo. The bow is faint and wide. Its curvature is gentle. It wraps around the shell like a distant boundary. The bow suggests the shell is pushing into a larger scale density gradient. It also suggests that material is piling up in a broad front. The front is not a thin rim. It is a thickened zone where mixing and cooling occur together. The physical detail is the front's smoothness. It lacks sharp knots. It is smeared as if stirred repeatedly. This indicates it is older and more mixed. A payoff arrives. The most enduring contribution of a shell may be not the bright rim. It may be the broad mixed front that merges into the cloud. That front is where enriched gas and dust are deposited into the medium. A limit of observation enters through dust and composition measurement. Dust emission depends on temperature and grain size. Different grain populations can mimic each other in brightness. Gas composition can be inferred from line ratios, yet line ratios depend on density and radiation field. Clumping can bias estimates. Cold dust can hide in dark lanes and emit weakly. Warm dust can dominate emission even if it is less mass. Distance uncertainties change inferred masses and temperatures. The limit is a limit of indirect inference and of model degeneracy. Multiple combinations of grain size distribution and heating can match the same broad infrared glow. Yet some conclusions remain stable. Dust lanes aligned with flow suggest real solids. Shadowed wakes behind knots suggest shielding and cooling pockets. Broad bows in the halo suggest merged material at larger scales. The closing image widens and calms. The bright rim is now only a small part of the frame. The halo spreads outward in faint streaks. Dark dust lanes weave through the glow. The bow-shaped front softens into the surrounding cloud field. Next, the story resolves toward the end of the arc. The shells are placed into a final calm perspective. The luminous blue variables' brief unstable phase becomes a gentle step in a much longer cycle of matter. The last view of a luminous blue variable shell is often quieter than the moment it first appears, because the shell keeps spreading even as its brightness softens. The final arc is that the shell becomes a gentle mixing layer, and then a faint memory in the surrounding medium. The opening image holds the nebula at wide scale. A thin oval glow sits in a dark field. The rim is no longer sharp. It is a broad band with uneven thickness. In places, the band looks braided. Two pale strands run side by side and then merge. In other places, the band breaks into a chain of faint arcs. Between arcs, the glow drops into a shallow shadow. The interior is not empty. It shows a low contrast haze. It contains wisps that curve like slow smoke. In that region, light behaves as a soft contour marker. Where gas and dust are slightly denser, the glow rises. Where the mixture is thinner, the glow fades. The first unlock is that the shell's end state is not a sudden stop. It is a gradual loss of contrast as pressures equalize and turbulence spreads material. The shell begins as a compressed sheet. It ends as a thickened region with no single boundary. A second unlock follows from memory and structure. Even after brightness weakens, shape persists. Filaments keep the outline for a long time. Dust lanes keep subtle shading. A broad bow in the outer halo keeps a direction. These remnants hold information about the environment the shell enters. The physical detail focuses on the braided rim. Each strand has a slightly different brightness. The inner strand is smoother. The outer strand is more ragged. Along the outer strand, small scallops remain visible. They are softer now. They look like shallow waves rather than sharp curls. The interior haze shows a faint gradient. One side is a little brighter. That side aligns with the earlier bright crescent. The asymmetry remains, but it is muted. Another visual anchor settles in. At one corner of the oval, a thin hook-shaped filament extends outward. It is faint but distinct. It curves and then thins into the background. The filament is a peeled layer. It forms where shear pulls part of the shell away. This feature delivers a payoff. The shell does not dissolve everywhere at once. It frays at weak points. It breaks where density, contrasts, and instabilities are strongest. The hook filament is a sign of that fraying. It also becomes a path for mixing. Along the hook, the glow is slightly warmer in tone. That suggests dust and cooler gas are more concentrated there. A third unlock moves inwards to the shell's thickness. As mixing grows, thickness increases. A thicker layer has lower peak brightness because the same mass spreads out. Yet thickness also means more total material along many lines of sight. The shell can remain detectable in some bands even when it looks dim in others. This depends on temperature and on the balance of dust scattering and gas emission. A payoff follows. Fading does not mean disappearance. It means a shift in which signals carry the structure. One primary number frames the timescale of visible persistence. A shell can remain recognizable for about 10,000 years, like a long, slow season compared with a single human lifetime. This number is only an order of magnitude guide. It depends on density and pressure around the shell. It also depends on how clumpy the shell is. Clumps hold contrast longer. Smooth sheets smear faster. The scale shift is gentle. 10,000 years is short compared with the life of a massive star. It is long compared with the time a bright flare would last. This is why the shell feels like slow motion. It is an afterimage drawn across many generations of motion in the gas. A new everyday analogy anchors the end state without repeating earlier ones. It is like a thin layer of cream poured into a calm cup of tea. At first, the cream forms sharp white swirls. Later, the swirls widen and soften. The cup never returns to pure tea. The cream becomes part of the whole. In a nebula, the shell is the cream layer. The surrounding medium is the tea. The mixing is slow. The pattern fades into a uniform tone. The analogy delivers another payoff. The most lasting change is not the visible swirl. It is the altered mixture that remains after the swirl is gone. Another checkpoint returns to what makes luminous blue variables special. Their eruptions are not steady winds alone. They can eject large amounts of mass and create dense shells. Those shells cool and fragment. They form dust and clumps under harsh radiation. They then interact with the surrounding medium. Each step converts a brief instability into a long-lived structure. The structure becomes a local environment. It shapes later flows and later cooling. It also becomes a record of conditions. The braided rim, the hook filament, the muted gradient all point to how the shell met resistance. Another visual anchor closes the journey. The oval glow is now barely above the background. Only the hook filament remains clearly traced. It points outward like a fading stroke of chalk. The rest is a soft oval shadow. Inside, faint wisps drift and dissolve. The rim strands merge into a single broad band and then into a haze. This delivers a final payoff. The shell's purpose is not to remain sharp, it is to move material outward and to share it with the medium. The record is written in shape for a time, then it is written in composition and cooling behavior. A limit of observation arrives with the faintness. At low surface brightness, background subtraction becomes uncertain. Confusion with unrelated clouds grows. Projection can blend multiple layers into one. Distance uncertainty affects inferred size and age. Grain temperature affects dust visibility. Clumping can hide mass in small knots that are too faint to detect. The limit is a limit of sensitivity and of separating one shell from the wider cloud field. Yet some aspects remain robust. A broad oval with a braided rim suggests layered expansion. A hook filament suggests shear and peeling. A muted gradient suggests persistent environmental asymmetry. The closing sentences settle into calm perspective. In that region, a signal would fade without vanishing. The shell becomes part of the surrounding medium and leaves a quiet enrichment behind. The story rests on a simple ending. Slow motion eruptions build shells. Shells cool, fragment and mix. The nebula's outline softens. The medium keeps the material and continues its long cycles.